Hi, welcome back to Statistics 1. We're up to lecture 21, and in this lecture I'd like to revisit some of the assumptions that we made throughout the course in all of the statistical procedures that we've conducted. So in a way you can look at this lecture as a little bit of review, and this week and the next week we'll do a lot of review to sort of recap what we've done throughout the semester. So what I've done is I've divided this lecture into just two segments. First, we'll review all of the assumptions that we made across all of the different statistical procedures that we've covered in this course. And then in the second segment, we'll talk about data transformations, which allow us to take non-normal distributions and make them normal so that we can still conduct a lot of the procedures that we've covered here in this course. So let's talk about some of the main assumptions in this first segment. So let's go all the way back to the beginning of the semester. At first we talked about different kinds of research methods, then we talked about how to do basic descriptive statistics, and then we got into correlation. And once we started doing correlational analyses, it's where assumptions started to play a role. So the main assumptions when we did correlation analysis were, one, a normal distribution in X and Y because we were looking at Pearson's product moment correlation, or that little r value. We assumed a linear relationship between X and Y, and we assumed homoskedasticity. And remember, the way to evaluate those assumptions, we looked at histograms to see if we had normal distributions. We looked at scatter plots to see if we had linear relationships and to evaluate homoskedasticity. And we could print the summary statistics and just look at the values of things like skew and kurtosis to determine if we had normal or non-normal distributions. We then moved from correlation to regression, right? Because if we have a correlation between two variables, X and Y, then I could use someone's score on X to predict their score on Y. So we moved from correlation to regression. A lot of the assumptions there stayed the same. So we're still assuming a normal distribution in the outcome variable Y. We are still assuming a linear relationship between X and Y. Again, we're assuming homoskedasticity. And we had an added assumption in regression that the correlations among the predictor variables didn't become too high. So typically we assume that the correlations among predictors are all below 0.8, typically even better if they're less than that. Because if you have correlations among predictors that are greater than 0.8, that could result in multicollinearity, which one is a problem because you probably have redundant predictors in your equation, but two, can create a problem in the calculation of the regression coefficients. And again, how did we test those assumptions? How did we look for violations of those assumptions? We plotted histograms to look for non-normal distributions. We looked at scatter plots and we looked at the residuals in the regression, so we could plot our residuals in histograms or in scatter plots. And we just looked at the summary statistics. After we went through multiple regression, remember we did mediation, moderation, then we moved to group comparisons. And we started out doing group comparisons by looking at t-tests. Again, when we were doing t-tests, we were still assuming a normal distribution in our outcome variable y, or there I tend to call it a dependent variable, because we moved from doing sort of correlational research to experimental research. When we were doing the independent t-test, we had this other assumption of homogeneity of variance. We're also assuming sort of equivalent sample size across groups. And we could test that homogeneity of variance assumption with Levene's test. We then moved from t-test to ANOVA. And we did between groups ANOVA and factorial ANOVAs. Again, you see that main assumption across all of these tests was the normal distribution in Y, or outcome measure, or dependent variable. We still have this homogeneity of variance assumption because in between groups and factorial ANOVA, we're getting that pooled error term, right? So if If we're pooling the standard deviations from all our groups, we're making this assumption that they're all relatively the same. So we would test that again with Levene's test. In the repeated measures ANOVA, again, we have the normal distribution assumption. Here we had that slightly different assumption called the sphericity assumption, which takes into account not only homogeneity of variance, but also homogeneity of covariance. And we tested that not just with Levene's, but also with Mauchly's test. Finally, when we got to the chi-square tests, we had just two assumptions: one, independence, and two, that there are adequate expected cell counts across our expected counts in our contingency tables. And those we could just eyeball to see if they satisfied the assumption. So if we look across all of those assumptions and all of the procedures that we covered in this course, there are two that really stand out that set some primary constraints on what we can and cannot do with the types of procedures that I've covered. So the two main constraints are this normal distribution in the outcome measure or dependent variable, and this assumption of a linear relationship between the predictor variables and the outcome variable. What if we can't satisfy those assumptions? What do we do? Well, there's a number of things you can do, and I'm going to cover some of those things in these last few lectures of this course. Today I'm going to talk about how do we handle non-normal distributions and talk a little bit more about how we detect normal versus non-normal. In lecture 23, we'll deal with the second constraint, that is linear relationships between the predictors and the outcome. That's where we'll talk about this more general mathematical framework called the generalized linear model. You already saw one example of how we can do that with binary logistic regression. In lecture 23, we'll look at other ways we can bypass this assumption of a linear relationship between the predictors and the outcome. But here I'm going to focus on this assumption of a normal distribution in Y. So we assume that there's a normal distribution in the outcome variable Y. Well, how do we test that? There are three main ways we could test that. The first way is just by eyeballing histograms and by looking at the summary statistics. The second way is by looking at what's called a QQ plot, which I'll show you an example of in a minute. And the third way is to conduct an empirical test, and these are rather rare, and I'm not going to cover them here in this lecture, but I just want to mention them. There's a few empirical tests. Probably the best known is D'Agostino's case-squared test. But they're very rare. It's unusual that we would employ them just to test this assumption, but I wanted to make you aware of them. You can Google empirical tests of normal distribution if you really want to get a test of this assumption. What's most common and is the easiest thing to do is just look at your histograms and look at your summary statistics. When you look at the histograms, which we'll do in a moment, you should be looking for extreme skew and or extreme kurtosis, that big peak. You should also be looking for outliers. And outliers in a univariate sense are often just described as a function of how many standard deviations is this case away from the sample mean. So a common rule of thumb is like 3 standard deviations. If an individual data point is 3 standard deviations away from the group mean, then we might want to consider that case an outlier and maybe drop it from our sample or trim it so that it's not creating such a large skew value. In terms of skew and kurtosis, if you just want to look at the summary statistics, remember you can get those in R with the describe function. A good rule of thumb is skew values greater than 3, absolute values of skew greater than 3, and kurtosis values greater than 10. Those are considered non-normal. So here's a distribution in a histogram. It's a positively skewed distribution, but it's due to just a couple of outliers. So there's just 3 cases out here that are way beyond the mean, which is about 30, right? So they're so far beyond the mean that I would just consider those outliers. I could just drop them or trim them, and then I wouldn't have that positive skew, and then I could make it a normal distribution. Here's a positively skewed distribution where it's not just these guys out here, it's that there's some more values, there's 4 more cases there that are all sort of trending in this positive direction. So now we have more of a positively skewed distribution that I can't fix just by dropping or trimming those outliers. Another way I could observe those is through this QQ plot, which is a plot of the sorted values from the data set against the expected values of the corresponding quantiles from the standard normal distribution. So a way to look at that in a normal distribution, it's a little bit hard to see perhaps, but what you see in a QQ plot when there's a normal distribution is this nice linear function with all of our data points, where we have our sampled quintiles against the theoretical quantiles. And they should form, again, this nice linear function. You can see that that's not the case in that last positively skewed distribution I showed you. Here we have this, what's looking like a nice trend, but then we have just a few cases way up here, so we clearly don't have a straight line in this QQ plot. That indicates that you have a non-normal distribution. So to wrap up this segment, all of the inferential statistics that we covered in this course involve several assumptions. Along the way, we saw that there are 2 primary assumptions that place big constraints on what we could do. That is the normal distribution assumption and the linear relationship assumption. How do we test for normal distributions? Well, we can look at histograms and summary statistics. We could look at these QQ plots, or there are empirical tests that you can also conduct.